Hello, in this video, we're going to talk about how we can use this idea of work being the integral of a force function to see how much work is done to stretch or compress a spring. First, we have four springs, Hooke's law. And Hooke's law says that the force required to maintain a spring stretched x units beyond its natural length is proportional to x, meaning there is some k, where k is just a constant called the spring function, where force equals that constant times x. So we can create our force function to go inside of our integral if we know k. So taking a look at some examples, suppose we know that a 200 Newton force is required to stretch and hold a spring 2 meters beyond its equilibrium position. How much work is required to compress the spring 1 meter from its equilibrium position? Assume Hooke's law is obeyed. So Hooke's law tells us that the force is going to be equal to some k times x. Well, the first sentence tells us that if the spring is being stretched 2 meters, then 200 newtons of force is being used. So here is F of 2 when it's being stretched 2 meters, and here is our x. So when stretching 2 meters, there is some value k that's getting to that 200 Newton force being required. Well, not hard to see, k must be 100, making our force function 100 times x. So that first sentence tells us how to get the function we're going to use. Now, how much work is required to compress the spring 1 meter from its equilibrium position? So our integral is going from 0 to a negative 1 meter, because we're compressing it, of this 100 x dx, because we're integrating force from that work. At this point, now it's just solving. This antiderivative is 50x squared by dividing by 2, being evaluated from 0 to negative 1, or 50 times negative 1 squared minus 50 times 0 squared, 50 joules. So it takes 50 joules of work to compress the spring 1 meter. Now, suppose we're given some slightly different information. That this first sentence for these spring problems, in general, going to get us at a way to find k. In this one, we're told how much work needs to be done to stretch from equilibrium position. Before, we were told how much force is used to stretch. Now we're told how much work is required. Well, we know work equals the integral of force. So 100 equals being stretched from equilibrium is 0 to 0.5 of Hooke's law tells us f of x equals some value k times x. So that goes inside our integral. We can now evaluate this. Say 100 equals K over 2x squared. That may be the formula you have seen many a time in physics, and integrals is why we see that formula over and over. And now we can plug in to x. Remember, these are with respect to x bounds. So we get K over 2 times 0.5 squared minus K over 2, 0 squared. This whole term here is just 0. So 100 equals K over 2 times 1/2 squared, or 200 equals K times 1/4. Or finally, K equals 800. So there is our spring constant for this function. So our spring constant gives us our force is 800x. First sentence tells us how to find K. Second sentence tells us where we're using that. Now we want to find how much work is required. Once again, work is the integral from A to B of force. So we are finding the work to stretch, so 0 to 1.5, the spring 1.5 meters of 800x dx. Integrating that, same process over and over, K x squared over 2. So 800 over 2 is 400. From 0 to 1.5. 1.5 is also 3/2. Or 400 times 3/2 squared minus 400 times 0 squared. 3/2 squared is 9/4. The 400 and the 4 cancel to be 100 times 9. Or 900 joules of work needed to stretch 1.5 meters, when 100 joules of work were needed to stretch 0.5 meters. So it's not a complete, it's not a linear function at all. You can't just triple the distance and get triple the work. We need to use these integrals in a step 1, find K, step 2, integrate. Right. In the next video, we will look at how we can use work to find how much, and how we can use integrals to find how much work is needed to lift an object.